Okay, so I'm going to repeat what I just said for Ellie and Bradley who aren't here. The take-home quiz goes out today. It's due Monday, December 2nd, which is after Thanksgiving. So, I mean, I'm giving it to you right now, so that way you could actually finish it before Thanksgiving, and you'll have it done. Awesome. There is homework associated with 1.5. There's homework associated with 1.4, 1.6, 1.7. Your test is the 5th of December, which is 2 weeks, exactly 2 weeks from today. So that's rad. We've covered 1.4. We're going to probably finish 1.5 today. It would be nice to, like, if we have everything done by the end of the second, we could have 2 days review for the test. That would be rad. So 1.5, parent functions and transformations. 1.4 is due on the day of the test. So 4, 5, 6, and 7, there's 4 assignments that are due on the day of the test. All right, so instead of having 1.4 part of the test you just took, it'll be part of this next one. And I'll give you guys the practice test probably maybe next Wednesday. Yeah, I just need to make it. All right, you have a question?
Yeah, is the test just 1.5 and above?
1.4 to 1.7.
Okay.
Since I did 1.1 to 1.3, 1.4 will be on the second part. All right, 1.5, parent functions transformations. A family of functions is a group of functions with graphs that display one or more similar characteristics. So that'd be a family of functions. A parent function is the simplest of the functions in a family. So for example, y equals x squared is the parent function for y equals negative 2 times x plus 1 squared minus 5. Another member of the family of functions for y equals x squared would be like y equals x squared plus 2. That's also part of the family of functions where y equals x squared is the parent. So we're going to go through a bunch of different parent functions that you should know. Awesome. So first, the constant function has the form f of x equals c, where c is any real number. The graph is a horizontal line. When c equals 0, f of x is the 0 function. What I want you to know from that, all right, what I want you to know is, what does f of x equal 3 look like? It's a flat line at y equals 3. It's just a flat line at y equals 3. I could have another function like f of x equals negative 5/3. It's just a flat line at a y value of negative 5/3. I could say f of x equals 1. Right, this is the same thing as saying y equals 1. All of these are a constant function. Cool, flat line. The identity function. If I'm going a little too fast, you're confused, just let me know. Ideally, this is review. The identity function is f of x equals x, aka y equals x. The identity function passes through all the points with coordinate a comma a. So it's y equals x. That would be the parent function. A member of the family is all the linear functions, right? So if I had f of x equals 3x plus 1, or if I had f of x equals x plus 1, these are all members of the family where the parent is the identity function. The identity function is just y equals x. That is the parent function of all our lines. Right? So this would be the parent, and then all the variations of lines is the same. Would be in the same family. Okay, so covering about a couple sections of Algebra 1. Here we go for x squared. These are the quadratic functions, right? Your parabolas. So the example here is x squared. I think we already talked about this one. So if I wanted to know what is, what do I want to say about this? Notice when you have a quadratic, both ends are in the same direction, right? It's a U-shaped graph, whether that U is facing up or facing down. It is going to be symmetric. Do you remember finding axis of symmetry? Right? Negative b over 2a, blah, blah, blah. Symmetric, and then both ends are always in the same direction. Not necessarily up, because if you have negative x squared, they both face down. So both ends, same direction. So I think it's section 6. I don't remember. No, it's chapter 2. Chapter 2 is when we're going to start dancing. Not dancing, just having arms. Yeah, chapter 2. And so I'll be asking about x squared. As funny as it looks, you will remember it, and it will serve you out on a test, and you'll remember end behavior. A cubic function, literally cube means the third. I forgot to say that the quadratic is an even function because it is symmetric across the y-axis. If I look at a cubic function, it's going to be odd. Yep, set you up. So it's going to be odd because it's symmetric across the origin. Right? The ends go in opposite direction. It's a big one I want you to see. Ends go in opposite direction. All right, so far, do you remember these four? Maybe not necessarily the names, but you like know what it looks like. So if I give you y equals 5, you know that's a flat line. If I give you y equals 5x, that's a line that goes up. It's diagonal. If I give you 5x squared, it's going to be a parabola. 5x cubed, it's a cubic. Looks like that, yeah. Square root and reciprocal parent function. So this is literally f of x equals square root, right? The second root. And throwback to maybe a week ago, we understand when I have y equals absolute value, square root of x. You know, under the radicand, it has to be greater than or equal to 0. Otherwise, you would be taking a square root of a negative number, and you don't want that. So notice this only exists on x values which make the radicand 0 or positive. So I'll write that out. So this is the square root function. Only second root. This doesn't include any other roots, third, anything above that. Only square root looks like this. Secretly, the fourth root, sixth root, all the even roots would look similar, but that's not like specifically saying square root function. The reciprocal function has the form 1 over x. So this is what I keep calling a hyperbola, because the hyperbole is in English. So hyperbola just swoops off to both edges. Notice that x cannot equal 0. Let me change the color so it's easier to see, because I'm going to draw a vertical asymptote. Notice I have a vertical asymptote at x equals 0. So VA, vertical asymptote. But wait, does someone have a good definition? What is an asymptote? What does it mean to be an asymptote? Yeah, the graph will get very, very close but not touch. So notice as I'm coming from the right side, right, my graph, I'm getting closer and closer and closer and closer, but I don't touch it and I like go up to infinity. And as I come from this other side, I get closer and closer and closer and I don't ever touch it and I go down to negative infinity. Also notice that where is y going to equal 0? For which x value is y equal to 0? Never. So this means we have a horizontal asymptote at y equals 0. So I have a horizontal asymptote as well. So it's chapter 2 when we're going to go through and like put all of this together and write horizontal asymptotes and et cetera, et cetera. Okay, so this is y equals 1 over x. One page down. 25 to go. Just kidding. All right, absolute value parent function. So the absolute value has absolute value signs, literally those bars. So it is, secretly, the absolute value is a piecewise function. And it's the graph is negative x if x is less than 0, and you graph y equals x if x is greater than 0. So you didn't even know that, but absolute value itself is a piecewise function. It is a v shape. Looks f of x equals absolute value of x. Notice that when I'm coming from the left, I have a negative slope, right? -1 is my slope until I reach 0, and then what is my slope? Yeah, and then my slope turns into +1. Do you remember how to draw absolute value graphs? Yeah, okay, it's literally a v. What if I have negative absolute value of x, right? A negative in front, flips upside down. I'm getting ahead of myself. That's like the next page. Cool. Let's see. So more or less, this is y equals -x, but only if x is less than 0. Otherwise, it would be y equals x, right? That's a slope of 1 with a y-intercept of 0, and this is when x is greater than or equal to 0. I don't know if you guys did this last year, greatest integer parent function. No? Did any of you guys take computer science or is in computer science right now? You? So remember, yeah? Okay. So I'm going to describe it to you guys, and then maybe you'll understand it. Otherwise, I'll just describe it for everyone. When you cast as an integer, what do? Chop off the decimal place, right? When you cast as an integer, it's literally called a floor function. Anyway, greatest integer parent function, what it is you're just getting rid of the decimal place. So if I have like 1.99, normally what do we round it to? 2. But the greatest integer parent function, also called a floor function, you chop off the decimal place, chop off decimal O, what would I graph y as? 1. So notice 1.99 is about right here, but I only graph it as 1. The moment I reach 2, I graph 2. So all the x values between 2 and 2.9999999 are graphed as y equals 2. So it's literally casting as an integer. You're taking a double. You're taking a number with decimal places, and all you're doing is just ignoring everything with the decimals, and you're just looking at the integer in front. You know how to cast as an integer? Yeah? Does that make sense? Yeah? 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 No? Okay. Thanks. I miss computer science. Honestly, I think that's my favorite class I've ever taught is computer science. Yeah. Okay, so greatest integer parent function, also called a floor. You're literally chopping off decimal. Okay, that's not math term. This is like Miss O'Brien term, chopping off decimal place. So you'll see this. One very oddly specific example of this is like a light switch. At what point do we actually have the lights on versus off? Like at what point do we have enough current flowing, right? At what point does it actually switch to being on? One of my friends is an electrical engineer, and so he has to deal with like certain voltages. Okay, well, you know, voltages aren't always constant, so there has to be like a certain number, so it doesn't matter if you're between these two, as long as it's between these two. Maybe this is too convoluted. Anyway, you see this in real life. A lot of times we ignore this, but if you have to know it, you'll learn it in college. Okay, that's all you need to know. Transformations of a parent function can affect the appearance of a parent graph. So transformations, you're changing the function, right? You're moving it, sliding it up and down, maybe making it wider, making it skinnier. So first is a translation. So I think of translation as like public transportation. You're literally moving from place to place, sliding, right? You're not being enlarged or whatever. Literally, translation, you're just transporting your graph, translating it across. You're not changing how wide it is. You're just moving it, sliding it up and down. Okay, so up, down, or left and right. Cool. Okay, vertical and horizontal translations. So in my intermediate class, the Algebra 2, we spent 2 whole days going through all these different graphs and understanding vertical and horizontal translations. So I'm hoping your Algebra 2 did the same. So normally we have, okay, so I'm going to do it in terms of parabolas. Y equals a times x minus h squared plus k. This is the vertex form of a parabola. Do you remember vertex form? Even if you're like, I don't remember until you wrote it, as long as you like see it and you're like, I know I've seen it before, that's all I really want you to do right now. As long as you have seen it before. So I'm going to explain what the 3 different letters mean, and then we'll go through. So this K, if you have an addition or subtraction at the very, very end, so it's not in the parentheses, it's not in the square root, it's not in the square, like it's not inside what's being actually like happening. So not inside the absolute value, not inside the root, not inside the square. It's just tacked on at the very, very end. That would be a vertical translation, up and down. So if K is negative, you're going down. If K is positive, you're going to be going up. No surprise. It's the same sign, right? If you're adding 2, move everything up by 2. Subtract 2 at the end, every single point in your graph down by 2. Versus horizontal. So horizontal is your H. Okay, so this is vertical. This is your horizontal. I always think of horizontal as the opposite way you would think. So if I would have something like y equals x minus 1 squared, you see the minus 1 and you would think, got it, left is negative. Just kidding. Horizontal is always the opposite of what you think. It's a trickster. So minus 1 means you're actually going to the right one, positive. So if you have a negative, if h is negative, it means you're going, well, they're talking about the actual sign. So if I have x minus 1s, that means I plugged in a 1 for h because this is a negative sign already. So if you plug in a positive number, that means you're going to be going to the right, meaning you'll have x minus whatever number, because you're plugging in a positive number while the actual vertex form is x minus the h. Yeah. And if you see it's like x plus a number squared, absolute value of x plus a number cubed, right? So the addition in the middle means you had plugged in a negative. So if you plugged in a negative number, you're going to the left. Okay, use the graph of f of x equals x cubed to graph each function. These are our translations, literally sliding up and down, not dilating it or stretching or compressing, just sliding it around. Use a graph of f of x equals x cubed to graph each function. Okay, think to yourself, don't say it out loud. What is the transformation of a compared to the regular parent function x cubed? Turn to the person next to you and discuss what you think is going to happen. Okay, so we see it's x cubed minus 3. One way to think about this is literally the same thing as saying f of x minus 3. So what I'm going to do is I'm going to graph my cube function. All right, what's 0 cubed? 0. If I plug in x equals 1, what's 1 cubed? 1. Let me plug in 2. What's 2 cubed? 8. All right, this is not a very good curve. So we are drawing the parent function. Did it say to draw? Use the graph to graph each function. Okay, so we're drawing the parent function first, and then we're going to use it to find our other, to actually draw g of x. All right, negative 1 cubed is just negative 1. Negative 2 times negative 2 times negative 2 is negative 8. Not surprising, it's symmetric with the origin. Okay, so this is f of x equals x cubed. And we just discussed how g of x is just going to be that same function minus 3. So I'm going to start at 0, 0. In my new function, I slide it down by 3 units. Then I go to 1, 1. And we said it's the same point, just 1, 2, 3 units down. Then I go to x equals 2, y equals 8. Same function, sliding 3 down. It's literally like oh my gosh, oh no, didn't mean to erase that one. It's like it's the exact same graph, just vertically shifted.
Hey, how did you know how much to move up?
Down by 3.
No, I mean, like, I get how you go, like, start at negative 3 and then go to the point above it, but what about the point that's at 2 and 5?
What about 2, 5?
Okay, never mind.
So how do I know?
It's cubed. It's the x cubed.
So I cube the x and then I subtract 3. I don't know why, I just can't draw right now. Okay, so I have that one. Come up here. Okay, that's close. Okay, I go to -1, comma -1, right? This point right here, you see where I'm pointing? And I have to go down 3. 1, 2, 3. Then I come to the other point, go down by 3. So I have a shaky hand right now, but this is close. You can see blue boy is moved down to pink, right? The blue is shifted by 3 down to the pink. So the one below, this is f of x equals x cubed minus 3. So we didn't go through and plug in all these points into x cubed minus 3. I used the parent function, right? So what I was drawing in the, like this pink stuff, you don't need, that's what I was like verbally saying to you to get the original points. I wasn't sure if you remembered the original points of the parent function. So all I did was I shifted down. So this next one, think, what is the transformation for b?
Into x.
Sorry, what's your question?
X cubed minus 3 is the transformation.
It's g of x. Right, g of x is the transformation because it's literally the original function down by 3. So h of x is another transformation of my parent function x cubed. So turn to the person next to you and discuss what is happening. How is it moving? Okay. Yep.
It's just what the parent function is. Would the parent function just be f of x or would it be x?
Parent function is
Is this the transformation or is this?
g of x is equal to this. This is the function of the transformation. All right, let's do this. Who wants to tell me? Robert, you look sure of yourself. Let's do it. Woo!
Sure. You go to the right 4, then up to it, and you draw them.
Okay, so here he says, okay, so to the right by 4. Let's do my check. So I see the negative. It always tells me trickster because it's inside the cube. So although I see a negative, it's not actually going negative. It's going to go 4 to the right. And then the 2 does what?
Goes up.
Exactly, up by 2. So this tells me how to move. First, I'm going to draw my parent function, and then I'll use the points of my parent function, and I'll shift all of them to the right by 4 and up by 2, and I'll have my new function. Okay, first, let's draw our parent function. I'm going to use the same color. 0, 0, 1 cubes 1, 2 cubes 8, -1 cubes -1, -2 cubes -8. It's just the same parent function of x cubed. Perfect. I have my points. Now I can shift them all. So my parent function is f of x, right? My parent function is the cube, x cubed. My transformation is this h of x, right? It's another function, but it's going to be a translation of x cubed. Every single point is to the right by 4, up by 2. So I'll first start at 0, 0. I go to the right by 4. So I go to x equals 4. And I have to go up by 2. So notice my 0, 0 is shifted to the right by 4 and up by 2. I'm not going to draw the arrows every time because it looks messy, but I won't leave them. I'll draw them, but I won't leave them. Okay, 1, 1. So I go over 4, up 2. So here's my new point. I don't know if this helps you or not. Okay, new point. Let's see, 2, 8. Go over 4, up 2. Here's my new point right here. New point.
Wait, do you go over 2 from your
Right by 4, so right 4, up by 2 of my original points. So I'm going to select -1, -1. Go right by 4. 1, 2, 3, 4, and up by 2. Shifting all of my points over 4, up by 2. Go to -2, -8. Go over 4, up by 2. No, I don't want that to erase. So here I see everything is to the right by 4 and up by 2. So you didn't necessarily have to draw your parent function. Another way to do this, so I'll show you over here, is if I list out my x and y, what? That's not blue. List out my x and y coordinates. All right, so -2, -1, 0, 1, 2, cube, -8, -1, 0, 1, 8. So I'm listing out the 5 points I've been using for my parent function. Now, I said I'm moving everything right by 4. So I can go and add 4 to all of these, and I would find my new coordinates. 3, 4, oops. Were you guys shown this way last year? Yeah? No? Okay, cool. How were you shown last year? Just the graphing? Cool. Up by 2, so I add 2 to everywhere. So then, like, these are the exact coordinates of my new function, right? The one that's on the right, the pink one. That's, if I didn't have this, that's how I could find it, right? You don't necessarily have to graph the parent function. You could use the points and then shift them like that. Okay, so 2 more things I want to say about this. So vertex form, literally, the vertex normally says 0, 0. But my vertex is shifted over 4 and up by 2. So my new vertex is at 4, 2. So this is literally your h, k. Your h is your x coordinate of your vertex. Your k is your y coordinate of your vertex. So normally vertex for a parabola, it's the bottom of the u. For your cube function, it's where you're switching. It's where it almost looks like it levels out and then goes back up. For your absolute value, it's the bottom of your v is your vertex. So all of the vertex forms are roughly similar. All right, so y equals a times absolute value of x minus h plus k. That would be for absolute value. Y equals a times x minus h squared plus k. That's for squared. Y equals a times x minus h cubed plus k. So that's vertex form for a cubic function. Notice they're all the same. The difference is, absolute value, parentheses and squared, parentheses and cubed. You see a pattern? Hopefully. Check, check. Okay. And then this is another way to explain how you know which way you're going. So if you set what's inside your parentheses equal to 0, and then solve for your x. So you see, it's actually moving over by 4. If I would have something like, let me do this, y equals x plus 1 squared plus 2, you set what's in the parentheses equal to 0, and you see, your shift is like opposite sign. That's another way to prove it to you. Okay, 2 pages done. Solid. Reflections in the coordinate axes. So we've kind of discussed this before. Remember I asked you, what does x squared look like? Up. Negative x squared faces down. The negative reflects it across the x-axis. So if you have a negative in front of your function, it will reflect it in the x-axis. Versus if you plug in a negative x, it reflects it in the y-axis. So it's kind of related to to test for y-axis symmetry. So if my graph actually looked, if this was actually my graph, right? It looked like a little bird that I drew in kindergarten, right? Like a V. If this was actually my graph, the way we tested for y-axis symmetry is we'd plug in negative x for x and we'd get the same graph. No, what we're talking about here is this is absolute value of x. That's what it looks like. If I say, if I plug in a negative x, then the absolute value would only be over here. Right? It literally would flip it across. So this is, the blue is showing before, the red is after. Right? The blue over here is showing before, the green is after. That's what it's trying to show you. It's not like one whole graph. Okay, let's start on the left side. f of x equals negative, f of x is the graph reflecting the x-axis. So for instance, this top one is f of x equals square root x. So if I put a negative in front of my function, here, this is f of x equals negative root x. Literally, you're just multiplying every single term by negative 1. And it reflects it across the x-axis. Because what used to be a positive y is now going to be a negative y. All right, reflection in the y-axis. So this graph, this is what I was just talking about, this would be f of x equals square root x. If I plug in negative x for x, the graph over here, let me switch colors, the graph right here would be f of x equals square root of negative x. So only the negative x values can you plug in to have a positive under the radical.
Why do the square roots of x look so different on both sides? It does the same thing.
It's like you're talking about the orange and the purple?
No, like for the left side, f of x equals the square root of x looks the same as the right side when it says f of x.
This is the same.
But why do they look different?
I don't know.
Okay.
They should be the same. I think it's because, have you guys ever looked at one of those pictures, the illusions, where it's like, ooh, which ball is bigger? Oh, well, it depends with the gradient. So here I think it depends because you have a graph under versus a graph to the side. Makes it look a little different. It's my hypothesis. Okay. So use the graphs f of x equals square root x to graph each function. Turn to the person next to you. Talk about how this negative root x plus 4, how is this different than just regular root x? How is this different? Turn to the person next to you. Okay, so this is going to be the graph of root x. So what did we decide? What's the difference going to be? Jesse, what do you think? So it's going up by 4 and, reflected. It's going to, instead of being, didn't we do this? Yeah. So instead of being up, it's going to be like swooping down. It's being reflected. Instead of coming up, it's going to be swooping down. Whatever, right? You take this, reflect it. It's going to be okay.
How did you know the coordinates were 0, 0, 1, 1?
So these are the coordinates for the parent graph of square root x. 0, square root 0, 0. And I picked nice numbers. Notice I didn't put square root 2. That's not a nice number. Guess what? 4 is nice, because what's the square root 4? 2. 9's nice. Square root 9, 3. I just picked the perfect squares. That way I have integer coordinates. Hey, okay. So I need to reflect my graph and then up by 4. So what I'm going to do, we have to do order of operations. Notice we are going to take square root x, multiply by negative 1 first, and then add 4. I just hit my elbow. I did this really hard yesterday on a table, and I couldn't feel my arm for like 20 minutes. Cool. Okay. I'm good. Did you say it's tight? Yeah, it's great. All right, so multiply by negative 1, and then we're going to add 4. So multiply by negative 1, and then add 4. Because technically, if I plug in an x value of 0, right, square root of 0 is 0 plus 4 is, 4. Then if I take square root 1, well, it's 1, negative 1 plus 4. So this, in orange, this whole list is showing what root x would be. So first I have to multiply it by 1, and then I can add 4. Okay. So my new coordinates. So I'm not shifting it horizontal at all. So this is 4, 3, 2, and 1. So I have a point at 0, 4, 1, 3, 4, 2, and 9, 1. So you can see instead of a movie theater arm, it's going to be a swooped and down. What's a better word than swooped and down? I don't know. A whoosh. So whoosh and down. Okay, cool. So whoosh down, and also that whoosh is now lifted up by 4. So now it's like overlapping. Because normally if I reflect it, it would look like this. But then I'm moving it up by 4. Ah, that is my new graph. That's pretty close. So I reflect it, and then I move it up by 4. That is what's happening. Cool. Let's try the next one. Give it a shot. Talk to the person next to you. See if you understand how this is a transformation of my regular root x function. Did you say brain overload? Today, you should feel like you're getting money's worth. You should feel that every day, but today especially. No, because I got here at 6:45. Lucky. I had a lot of stuff to do. I had so much to do. I'm teaching every single period today. I'm working with kids through bonus. I have a meeting during lunch, and then during my one free period, I'm going over to do start basketball. And then I'm going to be there till like 9. The game literally got over at like 9 last night because it was so long. This is why I have not, well, I started at 3. The first game, there's 4. This is why I haven't graded your test yet. But I did make your quizzes and printed them and had coffee. Okay, who wants to talk about what's happening here? Yeah.
It's reflected over the x-axis. It's going to the left one, and it's going up.
Okay, so there's 3 different things happening. So I'm going to draw my parent function. All right, 0, 0, square root 1 is 1, square root 4 is 2, square root 9 is 3. I picked the nice, easy numbers. Notice I didn't pick square root 5. I don't know what that is. 2.1, 2.2, who cares? Not a nice number. Let's only pick the nice ones that help us out and give us integer points. So I'm going to draw my x comma y. Here are the points I chose. Just the perfect squares. Okay. And then with my y values, so square root 1, 0, 1, 2, 3. So I have to go in order. So okay, let's talk about the x's first. So we have to shift everything left by 1. So that means I'm going to subtract 1 from my x's. Does this chart make sense? Like, I'm just taking the xy coordinates and I'm shifting them left and right, and reflecting just makes the y's negative before I like add it, before I shift it up and down. I don't know, I worry since you haven't seen this before. Okay. So I need to reflect it all, and then I'll add 2. So I have to go in order. I can't add 2 then reflect it. No, because it's multiplying by -1, then adding. PEMDAS, order of operations, multiply before you add. 2. So I have a point at -1, 2, -1, 2, 0, 1, 3, 0, and 9, -1. Okay, so you literally see, it's like I took the orange one, shifted left by 1, reflected it, and brought it up. And in that order, literally. You have the orange guy, shifted left by 1, reflect it, and then I shift it up. There you go. I'm a visual person. This is the way I see it. Yeah. Okay. All right, and so this is, we're just shifting, right? We've just been like moving it. So if I would, let me see if I can do this. So move it like this. Okay, so I shift it left by 1. Come on. Left by 1. I reflect it. Oh, is this not going to work? Nope. Damn it. Reflect it. So shift it left by 1. Reflect it. And then shift it up by 2. I don't know. Did you see that process? Okay, I drew it. Left by 1. Reflect. Up. Okay. I'm done with this. Okay, so let's take 2 seconds. Just like do some, what do you call it? Like Vinasa, sun things, whatever. You know what I mean? Yoga. Like, yes. Do a sun salutation. Do a little breathing exercise because you guys look like you're dead. Cool. Okay. Maybe like do the wave or something. Energy. We have 20 more minutes of class. Hey. Okay. Wonderful. Do you like stand up? I'm trying to give you a brain break. Oh, I know. I'll tell you a joke. Let's see. Yeah, I had a really good one. No, not a good one. Okay. Because this is gonna take some more big brain energy, so I just want to give you like a second to clear your mind, do some breathing, and then wake up. I read this whole like list of jokes. When I was a kid, I used to go around telling people jokes.
You know the monkey joke?
Huh?
You know the monkey joke?
Which one?
Why the monkey fell out of the tree?
Oh.
I don't know if I want to ask why. I do? Why?
Because it was dead.
What? Why? That's such an anti-comment.
Why did the second monkey fall out of the tree? Because it was tied to the first one.
I was gonna say that.
Oh, sorry.
Yeah. That reminds me of the joke. So these like 2 people are in the woods. This is like a dumb one. I was like, why would you say this to me? They like see this well and they want to know how deep it was. Who walks by a well and was like, how deep is it? I don't care. So they like found a pebble, they threw it down and like they didn't hear it and they're like, that's weird. So they grabbed a log and threw it down and they didn't hear it. They're like, that's weird. And then this is the way the joke was written. They find this engine block. Why is there an engine block in the middle of the forest? Anyway, they take the engine block, slide it there, and they like throw it down the well, push it down the well. And then, a little while later, they hear this thunk, and they're like, aha, we know how big it is. Thanks, physics. And then about a couple seconds later, this goat goes screaming fast past them and goes down the well, and they're like, that was weird. And then a farmer comes up, and he's like, have you seen my goat? And they're like, yeah, it's so weird. It fell down the well. And he's like, that's so weird, because it was tied to an engine block. What kind of joke is this? I was hoping for a funny one, not this. Yeah. Exactly. And why is there an engine block in the middle of the forest? Okay.
Well, no, I could get an engine block.
Because the goat will run away. My grandma had a goat when I was growing up, and it's so mean. It would like ram you, and the little poop pellets are everywhere.
I can just picture it when
It's probably one of the most Nebraska things I've said. My grandma had a goat. Okay, that was a nice like 2-3 minute of brain break. Okay, last joke, and then we'll get going.
Okay. What do you get when you squeeze a temple? What? Orange juice. You get it? Does no one get the joke? Because when you squeeze orange juice, you get orange juice.
If you have to explain the joke, it's not funny.
Thank you. Oh, okay.
I thought it's called a synagogue. Right? Am I wrong?
I mean, it is called that.
It is called a synagogue, okay.
It's also called a temple or school or whatever,
Okay. I learn something every day. Learn something every day. All right. That's bravo. I'm gonna tell that joke. Literally, I'm gonna the first coworker I see in there, I'm gonna tell this to them. I'll make sure they're Jewish when I tell them, and they'll be like, yeah. Okay. So here we go. We have talked about translations. That was a nice brain break. Hopefully, the toxins have left your brain and we're ready to work more. So, what? I don't know. You know how when you exercise, you build up lactic acid? When you think real hard, you build up probably something.
Brain acid.
Whatever. I know. I'm fully aware of the actual science. Exactly. Then there's no reason I should ever give a brain break again. All right. Vertical and horizontal dilation. So, if you guys go to the eye doctor, they literally will do this like test for glaucoma. right? They'll put these drops in your eye, and what happens to your pupil? Dilates. Okay, so something's dilating, it's getting bigger. So if a graph is being dilated, we're talking about stretching it, bigger or smaller. Okay. See, you guys know what these words mean, just maybe not in the context of math. So if I have, let's do a couple examples first. So I have f of x equals 3 times root x. This is a vertical dilation. Do you understand why? What is happening? It's being multiplied by 3. So it used to be a graph looking like this. It's now being multiplied by 3, so it's getting much steeper. It's literally being dilated vertically. It's being stretched vertically. What used to be a nice square root x is now being stretched vertically. Let me show what that looks like. Used to be square root x. Oops, hold on, that's not. This is what like root x would look like. Our new root x would be something like that. Because it's literally being multiplied by 3. Every single point is now 3 times higher. This is not exactly correct. Similar to that. Okay, vertical dilation. What if I have something like this? Let's say f of x equals absolute value of 5x. This is a horizontal dilation because it's inside the absolute value. It's inside the parentheses. If it's a, right, the one that's in front, the coefficient, not inside the parentheses, not inside the absolute value. If it's out front, vertical. Inside the stuff, it's going to be horizontal. So this is a horizontal dilation. Versus if I would have f of x equals 5 times absolute value of x, this is a vertical. If it's in front and outside the absolute value in parentheses versus inside the absolute value in parentheses, that's the difference. Okay, and that's a summary of what this page is going to talk about. Vertical and horizontal dilations. Vertical dilations. If a is a positive number, you're multiplying the whole function by it. What you're literally doing is you're expanding it or compressing it vertical. It just depends what you're multiplying by. If you're multiplying by a half, you're literally going to compress it vertically because every y value is now half of what it used to be, right? Let's try that again. So if you have y equals x squared and you multiply by 1/2, every single y value is now half of what it used to be. So it's going to be compressed vertically. If you multiply every number of x squared by 2, it's being expanded vertically, dilated vertically. It's being stretched vertically, right? So if you multiply everything by 2, everything is twice as high. So it's going to get a lot skinnier. That is what this left side is showing you. All right, if you are multiplying by a fraction between 0 and 1, it will be, because keep in mind, if I have a negative in front, all the negative does is flip it over the axis. Talking about the number itself. If it is a fraction, all your y values are going to be cut down. So it's going to be compressed vertically. If you have a number greater than 1 in front, it's going to be expanded vertically stretched. Similarly, if you have, so this is if you have the a inside your function, right? It's not just nice right outside of it. It's actually inside the function. It will be compressed or expanded horizontally. So if your number is between 0 and 1, it's going to be expanded horizontally. Because think about it, ready? If I multiply every y value by a half, it's going to half the y values, which means my horizontal, it's being pulled, right? Stretched horizontally. That's why it says expanded horizontally. Okay, let's do example 3. Identify the parent function f of x of my g of x. So here I have g of x equals negative absolute value 4x. What would the parent function be?
Square root of x.
It would just be f of x equals absolute value of x because it's just absolute value. Okay, done, check, identified. Identify how the graphs are related. Okay, so we just have to look how they're related. How would I get to g of x if I started with absolute value of x? What do I have to do?
You have to reflect across the x-axis.
Reflect around x-axis.
And compress it horizontally.
Exactly, and we're going to have a horizontal dilation.
Why would it be vertical? Oh, no.
Because it's inside the absolute value. Okay. So, let's go ahead and let's draw it. So, did my vertex move? Did I have a translation up or down, left or right? Did I have a translation? No. So, I'm still going to start at 0, 0. But we said that it's being reflected around the x-axis. So normally absolute value is a v pointing up. Being reflected is going to be a mountain, a v pointing down. And then the horizontal dilation means it's going to be 4 times compressed vertically. It's going to be 4 times. What's the word I'm looking for? Like thinner, 4 times thinner, 4 times. What used to be wide is now 1/4 the width of it used to be. So it used to be a nice V. That's gonna be a very like sharp V. Okay, so normally I would have a point at 1, 1, but I reflect it would be 1, -1. But then I have this dilation, so it'd be 1, -4. Now what would my next point be? Do we know?
2, -8.
Yeah. More or less, this 4 tells you what the slope would be of your 2 sides of your absolute value. So I also have a point at -1, -4, -2, -8. So this is 0, 0. This one is, let's see, 1, -4. So I'll show you in a moment. 1, -4, -1, -4. Cool, and that is our graph. So if you start with your, no, but I'm labeling it for you guys. They must be accurate. Like your graph has to be accurate. If you put it on the wrong point, then I think you don't know how to count. Okay. So my x values, I picked -1, 0, 1. And the y values originally, well, absolute value -1 is 1. Absolute value 0, 0. Absolute value of 1 is 1. And then I go through and I have to multiply it by 4 first. Then take the absolute value and multiply by -1. -4, 0, -4. So I had to multiply by 4 at the beginning. Because imagine if I inside had -4. Well, the absolute value would take care of the negative and make the negative go away. Yes?
So if you asked us to describe the type of change, we just say reflected constant.
And horizontal dilation?
Yeah.
And to be, yeah, exactly. So absolute value literally has the V, and that's what the graph will look like. Right, absolute value, that's what the graph looks like, just to be clear. And then if I have square root, looks like that. A little different. All right. So we're at the top of page 29. I think there's just a couple more examples. Is it like 2 pages? Yeah, exactly. Perfect. So first, identify the parent function. Then say how our translated function is related to the beginning. So what did I do to my parent to come up with my transformation? Then graph it. All right, so it's like 3 different things we're doing in this example. First, what is the parent function of g of x equals 1/4 x squared? What would my parent function be?
F of x equals x squared.
F of x equals x squared, just the square function, right? So parabolic, quadratic. What did I do? What do I have to do to my parent to make it be my transformation? What is my transformation here? Do we know?
It's horizontal expanding.
So it's, if this was how do I describe this? If this was like 1/2 x and then squared, if it's inside the parentheses, then it would be horizontal. But since it's not and it's in front, it would be vertical. So the change, it's going to be a vertical dilation. Right, so since it's out front and it's not like within the parentheses, this would be horizontal. But in front, It is just vertical. It's getting worse. Vertical. Okay, so I know what's happening. Literally every y value, I'm just going to multiply by a fourth, aka compressing it. My vertical dilation is actually not making it bigger, it's making it smaller. It's a vertical compression. So I'm going to pick a couple points for my parent graph, and then I'll have x, y values and plot it. So normally with square function, right, the quadratic, I pick the nice simple values around my vertex because you know what negative 2 squared, it's 4, 1 squared is 1, 0 squared is 0, 1 squared 1, and 2 squared is 4. Okay. So I have my points. Let me erase this so it's not confusing.
How do you know that off the top of your head that it's these points?
That is what it is. It is just these points. Yeah. So when you learn the parent function, the parabola is centered around 0, 0, the vertex 0, 0. So I pick the points right around it. So I pick 1 and -1 and like 2 and -2. I could technically pick like -3 and 3 and find the values are 9. These are always the ones I start with because that is for the parent function. Like those are the important ones near the vertex. And then we said to the change here is I'm multiplying all of these by a fourth. All right, so I'm going to go through and I'll multiply all of these by a fourth.
Also, when do you know to multiply like the x side or the y side?
So since this is a vertical dilation, I'm multiplying the vertical side, the y side. If I had a horizontal, I'd be multiplying the horizontal side. Yeah, because I believe this is what I had. This would be a horizontal dilation, and it would actually give you the same numbers. Yeah. Okay, so don't want that to confuse you, so I won't leave it on the notes. So I have a point at -2, 1.
The last one is 1, not 1.
What?
The last one is 1, not 1.
Sorry, yeah, I wrote it twice. -1, fourth, 0, 0, 1, fourth, 2, 1. So it's going to be pretty wide. Something like this. And if I would graph my parent function, like you would see, it is a vertical dilation. It's being vertically compressed.
Is that right?
What?
This wouldn't be smaller here.
What's smaller?
Well, because if you do it, for example, use the 0.6 on the x-axis.
0.6?
Yeah.
0.6?
If you use 0.6, it's way more inside.
What are you talking about, 0.6?
If you use x, like you know how you use your points, right?
Yes.
If you use 6 as one of the points,
Okay.
it's way smaller.
36 divided by 4 is 9. So if I put a -6 here, I have 36 times 1/4 is 9.
Yeah,
So at -6, so it should actually be something like -6, 9, which is here.
Yeah.
So I drew it way too wide. I mean, but like, you get what I'm saying. The point of this exercise is what is happening to my transformation versus the parent function. So I drew my exact points. 6, 9. Point is, I'm still getting like wider. I'm being vertically compressed. Okay, so that's a good point to stop. That means we'll finish 1.5 next time, and then we'll finish 1.5 next time, and then we could, how many more points? 1, 2, 3, 4. Cool. All right, I'll see you guys next week.
For this section,